Ladies and gentlemen, welcome to Wolfson if you haven't been here before. The college is 50 years old this year, and we are celebrating it. And one of the things we're doing to celebrate it is to have a set of lectures in which people who are connected with the college in various ways look back on what has happened in their professional fields during the years when Wolfson has been in existence. And tonight's a very special evening for lots of reasons. One of them is that from the outset, Wolfson's had a very strong connection with computing in Cambridge. And this lecture tonight commemorates that in a very special way. Our lecturer is Andrew Herbert, who started his research career in the University Computing Laboratory. He worked with Roger Needham, who was a notable, a very special early fellow of the college, and a major benefactor of Wolfson. And Andrew had the privilege of working on many of the seminal developments in computer operating systems and networks with Roger. Then he left the university for industry and founded his own company, which, in true Cambridge style, was eventually acquired by, in this case, Citrix Systems, a major American software vendor, which still retains a significant presence in Cambridge. In 2001, he rejoined Roger, who by then had founded Microsoft Research's laboratory in Cambridge. And he took over the directorship of that lab on Roger's untimely death. Subsequently, Andrew's role extended to become chairman for all of the Microsoft research laboratories and advanced technology centers in Europe, Middle East, and Africa, with additional responsibilities for technology strategy and policy engagement with government and industry partners. He retired from Microsoft in 2013 to spend more time restoring and reconstructing historical computers, not a single one of which runs Microsoft software. In particular, and this is very special for us, he's leading a project to reconstruct the Cambridge EDDSAT computer of 1949, which was the first machine to be built as a computing service for users rather than simply for specialists. And it's the first computer with a practical programming system. And he's brought with him this evening his personal portable computer. You see in front of you. It is portable. It simply requires 2 men and a van, but you can move it, and we have. Now, in addition to his passion for obsolete computers, Andrew is also devoted to elderly airplanes. He's currently restoring a 1930s Supermarine Walrus seaplane, and he flies around in his own 1953 RAF de Havilland Chipmunk trainer. So if you see him in the skies, wave to him and he'll flick his wings. He has been in turn an ordinary fellow, a senior member, and an extraordinary fellow of this college. He is presently our youngest Emeritus fellow. Ladies and gentlemen, Andrew Herbert.
Thank you, John, for those kind words. He also has a very indulgent wife who lets him get away with playing with his toys all the time. So my challenge in 50 minutes is to try and tell you about 50 years of history of computing over the lifespan of the college, and to link that to Cambridge itself, Cambridge developments that perhaps helped some of the advances and some of the Cambridge personalities. As I look around the room, I can see representatives from all the decades I propose to talk about from the computer lab. So I'm wondering whether I'm better just flicking through the slides, and like a Quaker meeting, people will rise and say something about that slide, like, that was me, or that didn't work that way. I hope those who know more than me will indulge me as I try to give an overview, and that's not too technical for those in the room who are not computer scientists, but sufficiently technical that those of you who are interested in computing know something about what is going on. I'm going to start with a little bit of prehistory just to set the context, and then when we get to the 1960s, the time the college was founded, I will come down and demonstrate this machine, as John said, my portable personal computer. It's an Elliott 903. It was probably built in about 1963 to 1965. It went to Aldermaston. It was sold by them in 1978, and the gentleman who bought it was in his 90s and wanted to find a good home, so it found its way into a spare room at our house. And there's Jane often says to people, it reminded her how large those early machines were. When I say, I just bring you home a mini computer, dear, but there you go. So let me start with the pre-electronic history of computing in Cambridge. And in fact, it goes back to Charles Babbage. He was a Cambridge graduate. In 1823, he conceived of a project to build a mechanical device, which he called a difference engine, to print out mathematical tables. In the 19th century, printed tables of the kind some of us will be familiar with as logarithms and trigonometrical ratios were the way in which calculations were done. They were important to navigators. They had navigation tables so that from their readings from sextants, they could calculate, and moon sightings and so forth, star angles, they could calculate their position. They're important to the Navy and to the Army for artillery calculations, so they could predict the fall of shot. They're important to many trades and industries. And so there was a huge industry in publishing useful tables, large volumes of them. Those tables were computed by hand. Indeed, in the 19th century, in fact, up until the Second World War, a computer was a person, typically a young female, who sat at a desk and did sums and wrote down the answers that were then printed in a set of tables that were given to someone else. Babbage's concept was he could build a mechanical device that would do that printing. It was called a difference engine because a way of calculating tables is if you have a formula to tell you how to advance from one number to the next, i.e. a difference, you can use that to automatically calculate the tables. And so he designed this machine. It was entirely mechanical. You turned one of the handles and it would produce tables. It was not only supposed to do the calculations, but also print out the answers in a tabulated form. Unfortunately, the money ran out. Many Cambridge startups have that experience. He did quite well. He managed to keep it going until 1842, and he'd secured £17,000 in total from the government, which, if you go back to the 19th century, is a large amount of money. But he never succeeded in getting the machine to work. There's a myth it's because Victorians couldn't build parts to the tolerance. That's not entirely true. I think it's more a case of he wasn't actually a very good project manager and contractors ran away with the money and didn't do the job for him. The machine does now exist. One of the Microsoft founders, Paul Allen, gave money to the Science Museum to fund a project to build two difference engines, one for them, one for him. And there is one in the London Science Museum. There's one in the Computer History Museum in California. The Californians turn the handle on theirs every week to demonstrate it. The British Science Museum doesn't seem to want to run theirs anymore. It's all about experiences rather than actually showing technology working. It's really rather a shame. And so that's quite an important machine. That set of figures, of tables, by the way, is from my set of 5-figure logarithms, which I still have in my desk drawer, but I have to admit to not having used them since probably 1972, and they are a bit creased and crumbled. So let's talk about the early beginnings of computing in Cambridge. I can't do that without starting with Alan Turing, particularly as you've probably all seen The Imitation Game as a film in recent months. Actually, Turing's not going to feature very much in what I have to say. My talk is going to be about engineering and technology, and that wasn't Turing's strength. Turing was a math student at King's College in the 1930s. He did some very important work in the theory of computation, which didn't actually get to be relevant until about the year 2000, when computing had caught up with needing those kind of theoretical ideas to advance further. But he established a couple of important principles. He established that a computer is in some sense a universal machine, and that all computers are in some sense equivalent, i.e. anything one computer can do can be done by another, and indeed one computer can simulate another. And indeed, when I'm working on programs for this machine at home, I tend to use my Macintosh because it's faster and easier and sits on my laptop to develop my programs using a simulator for that machine and then produce a paper tape. And there's a story about how you get a paper tape out of an Apple laptop, but I produce a paper tape to run the Elliott 903. And those theoretical results are actually quite important because they tell us about the power of computers and they tell us about what is important in the architecture of the machine. He also established one other result, which is that you can't write a program that can read in an arbitrary other program and tell you whether it will stop or not. And for a long time, that result stopped people trying to prove software correct. A few years ago, a colleague of mine in the Microsoft lab in Cambridge, Byron Cook, chose to revisit that question. Turing's result says, in the general case. Byron asked himself the question, what are the special cases? And it turned out to be that most of the programs that people write in modern programming languages actually fit the special case. And so you can prove termination for a lot of practical software. And in Microsoft, and indeed in Facebook and in others, there's a huge application now of automated theorem proving, treating programs as essentially a theorem and making sure the program can't crash, that it does the things it's supposed to do, which is a huge advance. And that was my allusion to it's only really in the last decade that Turing's results have been of interest to computer scientists, of practical computer scientists, as opposed to something of interest to mathematicians. Turing did design a machine of his own after the war. It was called the Pilot Ace. He never got to build it. It was built by a team at MPL, and actually, in the long run, it was a backwater. He had a rather different approach to programming compared to others, and it wasn't adopted or followed up to any great extent. So as an engineer, he wasn't an important contributor. To understand the engineering story of computing, we moved to the university's mathematical laboratory, which is in the anatomy school, which is now buried underneath the Lion Yard car park. On the left of that picture, although it's in black and white, is a famous green door. The green door is actually all that survives of that building. It's in the present computer laboratory. It's been preserved as a memorial. I and another colleague in the computer lab back in 1978 found it under the floor of one of the computer rooms, and we presented it to Maurice Wilkes, the head of department, when he retired. And ever since then, the lab has had a brass plaque on the front, and the names of anyone who was part of the original mathematical laboratory who subsequently retired are engraved on the green door, and it's mounted as an exhibit in the laboratory. So that door still survives, though the building doesn't. The mathematical laboratory was founded in 1937 as a university service to do calculations for scientists, engineers, and mathematicians. In those days, of course, this meant mechanical devices. And this picture here shows some of the early staff working with a machine built out of Meccano to solve what are called differential equations. And those are the equations that govern lots of physical systems, things bouncing on springs, pendulums, and so forth. They're all described by differential equations. And the basic idea was by connecting various rods and wheels together, the machine would move in an analogous way to the problem you were trying to solve. And if you attached a pen plotter to one of the wheels, it would draw a curve that represented what the system was doing. And that was pre-war analog computing. Well, during the war, the maths lab was taken over by the government, and the machines used for various wartime applications. The computer lab reopened in 1946 after the war, and a young man, in fact the chap standing at the back of that picture, Maurice Wilkes, who'd been an assistant, came back as the director. The chap who started the lab had gone off to Oxford. And Wilkes got to hear, through various contacts, an important professor of maths at the time, Hartree from Cambridge, then I think at Manchester, from a fellow called Comrie, who was the leading exponent of numerical methods for calculation. They'd got to hear of American wartime efforts on building electronic calculators, and told Wilkes about this, and he got to access some of the documentation. I think Comrie gave it to him, and he realized Cambridge needed an electronic calculator. In 1946, there was a summer school of all the Americans who'd worked on electronic calculations at the Moore School of Electronic Engineering at the University of Pennsylvania, and Wilkes managed to get an invite. He arrived 2 weeks late to the start of the course, but that was okay because the first 2 weeks were about numerical methods, and he knew that. The students were rebelling and were insisting that these people told them about the electronics because they want to understand how to build machines rather than know about the mathematical methods. So he arrived just in time for some of the people who worked on an American machine called ENIAC to talk about their ideas. And in particular, a man called John van Neumann talked about his ideas for what he called a stored program computer, which is the kind of computer we understand today. Wilkes lapped up that knowledge. On his journey back on the Queen Mary, he sketched out the design for a machine for Cambridge, which he named the Electronic Delay Storage Automatic Calculator, or EDDSAT, and that's a picture of it there. And that was Cambridge's first machine. The important thing about EDDSAT was that Wilkes conceived of it as something the mathematical laboratory would build and run as a service. Everyone else at that time who was exploring computers saw them as science and engineering experiments. And so they were trying to build bigger, faster, or exploring different ways of organizing computing circuits. Wilkes just sat down and said, how can I build a simple machine that will do sums for my users in the university? And so the claim for EDDSAT, which ran its first program on the 6th of May 1949, is it was the world's first practical computer. It was built for people to use, as opposed to be a laboratory experiment. And for that reason, it was extremely important. It was very influential. The mathematical laboratory ran summer schools that were attended by people from other institutions who wanted to learn about computing, who were designing computers of their own. And really those summer schools were where the British computing industry and the British computing academia were created. If you look at the heads of all the computer departments and laboratories in the 1950s and 60s, they'd all been through those summer schools. And so that was extremely important. EDDSAT is a beast. It contains 3,000 theomonic vowels. They're the glass bottles the older amongst us might remember inside televisions and radios. It's pretty heavy. It weighs 2 tons. It occupies an area about 20 feet by 20 feet, so physically quite immense, and it consumes 11 kilowatts of heat. 11 kilowatts electrical power, which then come out as heat. That's one reason why we didn't bring EDDSAT here, because if we turn that on, you'd all be cooked very quickly. As John said at the beginning, I have the privilege of running a project which is building a replica at the National Museum at Bletchley Park, National Museum of Computing at Bletchley Park, and indeed there's a row of my volunteers sitting down there. And I do hope that those of you interested in following up do come across to Bletchley Park and see the machine. We're hoping it will be in a state to start doing calculations by about the end of the year. It won't be complete at that point, and there's still a lot more work to do on getting the exact replica, but we're making amazing progress, and it's been quite exciting. Very little of the original survived. Very few drawings survived of circuit diagrams and so forth. Fortunately, there were a good number of photographs, and there were some technical papers. So the team who've been working on this project have essentially been doing forensic engineering of working back from the photographs to what might be a circuit that would let you lay out the vowels that way, and how would you use that circuit to do some kind of computing function, like adding numbers or driving the memory. And that's been a very challenging task. We're fortunate that amongst the volunteers, there are a few folks, grey-haired or balding, who grew up in the era of vowels and worked on some of the valve machines of the 1950s, and their expertise has been very valuable. The rest of us are of the transistor age. Transistor experience, you can sort of work back into vowels, but you do have to remember that vowels bite. They work at 250 volts, whereas this thing runs at 6 volts. The big challenge that people like Maurice Wilkes had in designing EDDSAT was memory. In a modern machine, the memory is built of electronics, transistors, and we know we can pack lots of transistors into a silicon chip. You can't build memory out of vowels. It takes 7 vowels to remember a single 1 or 0. So if you scale that up to just a few thousand words of memory, not the megabytes or the gigabytes you buy for your machines today, you're talking about hundreds of thousands of vowels. That's a huge physical area, it's a huge amount of electricity, and at that number of vowels, their reliability isn't good enough, and you're likely to always be fixing faults. So they had to use something else. What Wilkes used, based on his wartime experience, were 5-foot-long metal tubes filled with mercury. And the basic idea was when the computer wanted to remember a number, it would send the 1s and 0s as a train of pulses down the mercury tube. And because those pulses travel through mercury at the speed of sound, which is much slower than the speed of light, which is the speed at which electrical circuits work, essentially there was a delay, hence the delay storage bit of EDDSAT, and you could fill these tubes up with data. When it dribbled out the end, you could circulate it back round, and so electrically you could keep information in that mercury tube until the computer needed it for the next step in the calculation. A very expensive technology, a very temperamental technology. Those mercury tubes are sensitive to temperature, and so the engineers were always changing the speed of the clock on the computer to match it to the speed at which the information was going around in the memory. and it was generally a bit of a nightmare. Things had to improve. So the two pioneers who led much of the EDDSAT work were Maurice Wilkes, that young man. This is Wilkes in the, I think, 1990s. He became head of the computer laboratory as the maths lab renamed itself, I think, in the mid-60s. Wilkes conceived of the EDDSAT project and sketched the early design. He was actually very dependent on a very competent engineering team that he built, who took those sketches and turned it into a practical working machine. Our replica is intercepting EDDSAT as it would be in about 1950, which is an early stage, and we know from the records quite a few things were marginal, and over its life it lasted till about 1956. They kept making continual improvements. Indeed, the chief engineer commented that when it first worked, it only did so by the skin of its teeth, and so we're going to have all those challenges with our machine too. The person on the right of the picture is David Wheeler. Wheeler was Wilkes' first research student, and Wilkes gave Wheeler the challenge of designing the programming system when no one knew what programming was. And I'll talk a little bit more about that. Indeed, many of Wheeler's ideas show up in the way this Elliott 903 is programmed. But really, Wheeler deserves the credit for inventing the modern concept of software and programming, the idea of building programs out of reusable pieces of code called subroutines. That's all written up in his thesis. So to give you some examples of what EDDSAT looked like, this was the user interface. You fed your programs in on paper tape, thin strips of paper with punch holes in them. The machine would read in the program, it would run your program quite slowly. EDDSAT ran at about 650 instructions a second. A modern machine is running at hundreds of millions of instructions a second. But remember, EDDSAT was competing with people with pen and paper and with hand calculators. So it was about 1,500 times faster than the hand methods. Your output appeared on a teleprinter and chattered out quite slowly. While the machine was running, you had those oscilloscopes. You could see the contents of the memory, and they would gently twinkle as the machine was manipulating numbers and running through its program. So to write your programs, you sketched your program out on a piece of paper. The notation was very simple. You programmed the machine's electronics directly. There were no high-level languages like Java and Python you might have heard people talk about. For example, the A instruction was add. So if you wanted to add something into the machine's central accumulator, you wrote A. And if the number you wanted to add was in the 5th location of memory, you wrote A5. If you want to subtract, you wrote S. And so the thing was quite mnemonic. When you pressed the start button on EDDSAT, the machine automatically read in the paper tape and translated those alphabetic codes and numbers into the internal binary of the machine. And when it reached the end of your tape, it would then go to the start of your program and produce the output. And so what we have here is someone's coding sheet written out by hand as they were programming. You then punch that on paper tape. In EDDSAT, they used 5-hole tape. That was what the telegram network used for transmission from post offices and exchanges, and used exactly their code. And you can see someone stuck the paper tape down on a piece of paper and tracked how the binary codes map back to the letters. Of course, someone had to punch that paper tape. That was typically the job of a computer operator, typically a female in those days, and would be a touch typist. So unlike a modern machine, you didn't see on the screen what you were typing as you input. The deal was you punched the tape once, you then put it into a reader, and you punched a second tape to the same script, and the reader would check the second punching was the same as the first. And if you had 2 tapes that are identical, then the chances were both tapes were what you thought they were. If there was a difference, the machine would stop, and you would look at the 2 paper tapes and compare the pattern of holes and choose which one you want or type the correct character. So the early programmers didn't have a screen on which they were seeing their word processing or their program editing as they were doing it. And then your output appeared just as tables of numbers. And again, the teleprinters were quite limited. They were very slow. They could print about 6 to 7 characters a second. So you didn't waste time printing out nice headings or even laying out your numbers very neatly. You went back afterwards and annotated it by hand with pen to say what was going on. So it seems very primitive, but to take another pot shot at Turing, The Cambridge team's approach to programming was much easier. Turing, by the time that the Cambridge people were working on EDDSAT, was at Manchester University, and he was programming one of their machines. Turing's approach to programming was that programmers should be intelligent people. You knew the binary numbers inside the machine that represented the computer instructions. So you have on the left a Turing program. You wrote down those binary numbers. You divided them up into groups of 5, and then you remembered off the top of your head which character on the Teleprinter code corresponded to that pattern of 1s and 0s, and you wrote that code. So though the Turing code does have letters and numbers in it, it's not mnemonic. It's not A means add, S means subtract, 5 means location 5. You are literally almost punching the paper tape by hand. Not very productive, very confusing. Modern programmers would not accept something like that. On the right is a piece of David Wheeler code with annotation, much more descriptive, much easier to understand. And that really was the Cambridge success. EDDSAT was not the biggest machine, it was not the fastest machine, it was not the first machine, but it was programmable and usable. And the other secret ingredient was that they wrote a very large library of useful software routines to solve mathematical functions. So if you're a physicist who came into the maths lab and asked how to program a solution to some equation you wanted solved, you'd be told, oh, use this routine to read in your numbers, use this routine to do your integration or your differentiation, use this routine to print out your results, and you just have to write a few instructions to glue all that together. Which is actually a very modern concept of software reuse, which is how programmers work today. Very few people write a program completely from beginning to end. They usually glue lots of pieces together from other people. So we are now getting close to the era of the foundation of Wolfson. After early machines like EDDSAT, by the mid-1950s, a British computer industry had sprung up and was building machines. Cambridge still built its own next machine called EDDSAT-2. This is a famous picture of EDDSAT-2. All the users are lining up to take their turn at using it. It was a personal computer, but only for 5 minutes at a time. When you had the machine to yourself, you loaded your program and your data, you got your output, and you went away. If you spent too long fooling around or trying to debug your program or it produced rubbish results, the users standing behind you would glare at you and stamp their feet and generally encourage you to go away and improve what you were doing. So that's the world's first job queue. Again, EDDSAT-2 was not the biggest or the fastest of its time, although there are a number of key computer architecture ideas that were invented by Wilkes and Wheeler, which feature in modern microprocessors. For the more technical people, the concept of microprogramming was invented in EDDSAT, that you build a complicated computer by having a very small, fast one inside it that, applying Turing's result, simulates the more complicated one you want the programmers to see. And that made EDDSAT very flexible. By the time we get to the 1960s, it was no longer really feasible for a university, even one of the size and competence of Cambridge, to build a central computer all by itself. And so the next machine, which was called Titan, was a collaborative project with a company called Franti. At that stage, Franti were selling machines commercially. With Manchester University, they had developed a supercomputer for its age, probably the power of a modern digital watch. It was a very fast machine, but very expensive, cost over £1 million in its day, and Cambridge couldn't afford to buy one of those. So a deal was struck that Cambridge would work with Franti and reusing Atlas circuits and Atlas parts, like tape readers and magnetic tape drives and so forth, build a more economical machine and apply Cambridge ideas to making it as efficient as they could. And so that was the genesis of Titan as a hardware project, which was a side that Wilkes and Wheeler remained quite heavily involved in. The Cambridge team also wanted to write their own operating system for it. By then, the idea that multiple people might be using the machine simultaneously and you'd schedule work and so forth had been invented. And so that was a big focus. There was a technical innovation in Titan that impacts modern machines. David Wheeler realized that Titan would be slow because they were using a much slower memory than Atlas. And how could he speed that up? He had the idea of building a very small but very fast memory in transistors, and that when your program was running, typically a program's sit in very small loops doing something, then they go to the next loop. If you could capture those bits of program that are running just now in that very fast memory, then the executing part of your program will be nice and fast, and the rest of it is sitting out in the slower memory waiting to run. And now when you go and buy yourself your Macintosh or your Windows machine, the salesperson will try and tell you about how much level 1 and level 2 cache you've got and why it's all wonderful. That salesperson is selling you slave store. The irony is it didn't actually work terribly well in Titan, but the concept was a good one, and later machines improved it. This is where Roger Needham enters the story. Roger came to Cambridge as originally a maths undergraduate, but by the end of his first year, he'd had enough of mathematics and moved into philosophy, and developed an interest in linguistics, and in particular in machine translation in the early 1950s. There was a lot of funding for machine translation in the early 1950s, particularly translating Russian to English and vice versa. And so he got involved in that. He started writing computer programs and gradually moved into the team that developed the operating system for the Titan machine, and ultimately became the leader of that team. I don't believe it was ever a formal appointment. I just think the group he worked with recognized he was a natural leader, and he sort of emerged over time. And indeed, many computer lab projects have that property. Wilkes would conceive of something and produce a half-baked design. A batch of people would start working on it, and someone in that team would take the leadership role and make it happen. And what emerged would match the title of Wilkes's concept, but not the original design sketch, but usually be a worthwhile thing. And really, I think Wilkes's claim to fame was his ability to spot good projects early, to find the right people to work on them, and then challenge them by building a half-baked version, then leave them to get on and build the correct thing and make it work properly. And that's very much the way in which Roger carried on making things working. That work on Titan established Roger as a leading figure in the world of operating systems. Wilkes had got to hear of an American development called time sharing. And this was the idea that you could sit users at lots of teleprinter terminals, and they could all connect into the central university mainframe as if it was their own personal computer. You divided the big machine up into little chunks of time and memory, and then they had shared use of that machine. So rather than waiting for your job to run in the job queue, you could be computing all the time. Of course, if the machine was shared, you ended up with a somewhat slower machine, but by this stage, the computers were getting bigger and faster, and so what you ended up with was like the machine you had previously. And so that was a reasonable trade-off. And Wilkes heard about this and said to the Titan team that he wanted Titan to do time sharing. And they developed the Titan multi-access system. It was very successful and much loved in the university. And it gave people the kind of interface that's carried through to the modern personal computer. Obviously, theirs was the world of a keyboard and a teleprinter as opposed to a keyboard and a screen. But you would keep your data, your programs, your text on the computer. That was stored on computer disks. You would go to the terminal, you could edit your program, you could run jobs that would run data through your program, the output would appear on line printers. And that was very much the world of computing that I knew when I was first introduced to it as a schoolboy in 1968. The next project that Roger worked on was one where I appeared as a PhD student, called the CAP computer. CAP was addressing one of the things that had bedeviled the Titan effort. Titan was programmed in that low-level machine code because you want the operating system to be as efficient as possible, and it has to control the machine. The trouble with that is it's very easy to make mistakes in machine code, and if you have a mistake in the operating system, the machine runs amok, people's programs don't run properly, data gets destroyed, it's all a bit of a disaster. So Wilkes and Needham conceived of a machine where the hardware was significantly redesigned so that you would write the operating system as a tiny kernel that could be trusted, that only did very basic, simple things, and every other part of the operating system, like the filing of users' files, printing, running user programs, each of those ran in their own piece of memory isolated from every other piece of memory in the jargon of protection domain. And that gives you a very resilient architecture. The irony is, by the time we finished that project in about 1978, we weren't solving the world's problem, because there had been advances in programming languages during that period, which had meant that people were writing operating systems in much more advanced languages where you didn't make the kind of mistakes in assembly code. So those of us who'd worked on CAT when we finished the project were kind of a bit frustrated that we'd solved the right problem at the wrong time. However, if you wind the clock forward to the modern age, where organizations have large data centers, where computers have got so large, particularly the server machines, that we carve them up into pieces, particularly with this cloud computing you may have heard of. We want to be able to take a large machine, run lots of different people's software from different organizations, and not have it interfere with each other. Magically, all those ideas have come back. It's now called virtualization, and one of the things that greatly amuses me is all the modern research students who don't understand there was a world before the web keep saying they can't find my thesis on the web. Well, there's a very simple reason for that. Jane typed it on a piece of paper. There's my copy, there's the university library copy, there may be one in the CUDA lab library. But we have now scanned it. But it is essentially a thesis about microkernels and virtualization, and you can still get a PhD for doing that. But these days, you can't write an operating system in 25,000 lines of code in the 3 years of a PhD period. So to give an idea of what computing was like in the 60s and 70s, I'm going to come and show you some stuff on this Elliott 903, the machine in front of me. I first met a machine like this as a 16-year-old schoolboy. Our maths master started a computer club, and the deal was we could send paper tapes through the post to the local technical college, where, we would send our coding forms to the technical college, where they'd be punched onto paper tape, the program run, and you get the results back the week later. You learn not to make programming mistakes when you get to change your program once a week. It's quite a different discipline. So I'm going to come around to the front and show some of the things on this machine. This is a bit like one of those don't work with children animals moments. We're in business. I've left my pointing stick behind, which I need. Excuse me a second. The first thing to say about the machine when it turns on is firstly how noisy it is. That's because it has fans inside it to keep the circuits cool. It's made using transistors, as all the 60s and 70s machines were. The screen has lit up. This screen is an anachronism. This is a 1980s terminal. What I should have on the machine, is this going to work? Yes. Is a Teleprinter device. I've got two of those in my workshop. They are not quite working yet. So I bought this for convenience. So you have to imagine this is one of those, and it's very noisy. It's going chunter, 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 clatter, clatter, clatter. When the machine comes on, this just says I'm a VT220 terminal. There is no operating system saying what do you want to do or log in. It's a completely bare machine. So if I want to program it, I come to the operator's console. The computer operator is now a long dead species. And I can program the machine by hand if I know the binary numbers. So I happen to know with this machine that a 15 is an input instruction and a 1528 reads from a paper tape reader. If I enter that into the machine and I store it, which is an instruction 5 in location 8, and I obey that, and I know that a 8 instruction is a jump, and I ask it to jump to location 8, and I enter that, and I store it in location 9, 5, 9, and I obey that. I've stored 2 instructions in the machine, and if I've got this right, I turn the tape reader on, and I jump to location 8. I've written a program that reads paper tape indefinitely, and you can see the lights flashing. Now, that's not a very productive way of programming a machine. If I wanted to write a very large computation, it would take me forever to key everything in like that. But that was where computing was at about the time of ENIAC. Rather than using hand switches, you plug things together with wires. The early Manchester machines, you program those by putting things in through the hand switch. the next development was to put in the machine something called initial instructions, which is a program that would know how to read binary numbers off a paper tape and put those in the memory of the machine and then run that as a program. So that takes me to the next step. And I need to click this on. That was the blank screen. There's the control panel. That was the 152048. And this is the binary tape. What I'm showing on this screen, there's my pointer. That's the one I want. Doesn't show up on a TV screen. That pattern of holes where X's mean tape, 0 means I punched a hole. Turns out that binary number, that's my 15208. Those 3 rows of tape turn to that binary number, that's my 88. So that's kind of Turing programming. I can write a paper tape like that. If you're an Elliott programmer, you know the initial instructions live at location 8181. And you know what that is in binary. So you set it on the switches and you press jump and your program reads in. And then I know my program starts at location 32, so I can run my program, and you'll see coming out on the screen a table of squares. Now, everyone who learns to program today, their first program prints out Hello World. That's a 1968 innovation with the Unix operating system, where the first program printed Hello World. Anyone who learned to program before then, your first program was a table of numbers and their squares, and that was because that was EDDSAT's first program. And so the first program I got to write was a table of squares. And so I've input a program as binary. And indeed, I can punch paper tape. The vendors sold these kind of devices. You can put a paper tape in underneath this thing, and using these devices, you can punch holes in it. So you can pass that one round. And going around this way, you can have some paper tape. We did other things with paper tape. So remember which tape was which. You could print patterns that were legible. And so that, for example, says Wolfson. And there's a few more of those people can come and retrieve afterwards. You want something a bit more productive, and so the next stage was to move to like the EDDSAT system and be able to write your program in something a bit more mnemonic. Let me get this tape loaded. You'll see just how much time in the 1960s the machine was hanging around waiting for the operator to do things. Now, where I'm going to go to next is here. This is a bit like the EDDSAT notation. The instructions are given by numbers, and you heard me mumbling the numbers as I was working the hand keys. This is the program in machine code to print out the table of squares. It says pick up 0, put it in a memory location I'm going to call X, print X, pick X up, 12 is the multiply instruction. Multiply instruction shifts the answer down the wrong end of the accumulator, so bring it back with a shift, and then use the Q out routine to print the square. Advance X, check if X is less than 10, and if it is, go back round the loop. So that's simple machine code programming. That's very, very close to the EDDSAT notation. So what I've just loaded is called an assembler, which is a program that knows how to read that stuff. And this is the squares program written out on a paper tape. If I feed this in, and I know, oh, there's jumped ahead of me, I pushed the button. I know to assemble a program, I jump to 8. I need the punch turned on. You'll observe it's not reading the tape so quickly, because as it picks up each line, it's having to think about what it means and translate it into the internal code. So the machine is actually now doing some real computing. And what it's put up on the screen, it's told me it's found my program called square, it's put it in location 32, it's put that location loop on the program in 36, but it can't find these things called Q out 1 and QD out. That's because they're library routines, just like EDDSAT. So I would then go to the library cupboard, pick up the appropriate library routine, which fortunately is in the right order on the tapes, load that in the machine, and I know to load a library routine. I jump into the system at 11. And now it's reading in my library. You see this is a little bit faster because the library is held in a slightly encoded form, so it doesn't have to be translated every time. The reason it keeps stopping is it's printing out on the screen where it's putting the various bits of the library in the memory machine. So that's useful for me to know. So I've now got a program. It's told me that program is complete. And I know the program starts at location 32. So if I jump to location 32, missed. Then what comes out on the screen is my table of squares. So that was called assembly code programming. That was how we worked in the earlier stages. You had to understand precisely how to program the machine. But it was a big advance over entering things in through the hand keys. Now I'm going to start the next tape loading and then talk over it, because this one's a bit thicker. The next advance, and this was really where much of the action was in research in the 1960s and 70s, was the invention of programming languages so that you could write your software in something much higher level that was closer to your problem. The language I'm loading here is called Algol 60. It's the ancestor of the Javas and the Pythons and the Cs that people use today. This is my table of squares program yet again, but it's now much more readable. So a mathematician, it makes quite clear sense. It says take x, start at 0, keep counting up till 10, print x, and on the same line print x times x. Very readable. So the idea with programming languages was to start expressing your problem in a notation that was much more in the world of the problem than in the world of the machine. That made you more productive. Although that's a tiny example, there's a lot more structure in that than the assembly code. The loop is explicitly written out rather than remembering about jumping around inside the program. And so the software system can do a lot more checking that your program is actually correct. And this is seen as the advantage of high-level languages. The disadvantages are to do all that. It's a much bigger program, which is why it's still reading it in while I waffle on. And as we see when we run it, it doesn't run as fast. So that was the start of a trade-off between stick with assembly code and run things very quickly, work in a high-level language, you get your answers out faster, but not necessarily you get through the development process faster, but the running program wouldn't be as quick. While this continues to go in, a few more things to say about the machine. This machine, when new in 1965, probably cost about £30,000. So you can multiply that by 10 in today's prices, at least. Typically sold to colleges, university departments, industry research labs as a general purpose computing platform. It's not that fast, but again, it was still competing with graduates with log tables and slide rules. They made about 1,000 of them. 6 survive, of which at any point in time 4 are working, and I threw a double 6 this morning, so I'm in good shape. And you can see them at various computer museums. 3 of them are in private hands, 3 of them are in museums. Now I want my Algol program. The good news is the tapes are getting smaller. That Algol program is literally just that, so it's much shorter. And of course, this would have been typed on the Teleprinter beforehand. So this process I'm going through now is that even this is speeding it up. To run an Algol program, I know to translate my program, I go to 8, and it starts to read in my program, and I should start to see some gibberish up here. I don't think it liked that. Let's try again. No, I think the machine is going to sulk on me. Right. we'll abandon it at that point. What it would have done if it had been working was show you that it compiled my program, and then when I ran the program, it would have printed out the same table of numbers. I'm not going to waste lecture time trying to debug and fix the machine. What do we do once a visual output? We use this thing, which is called a graph plotter. It's basically a pen that goes backwards and forwards over a drum that twists, and with that, you can produce nice, pretty graphs. And that was the nearest we got to visual output, so that can find its way around. There's one for each side. There's a couple other things that can wander around the room. I'll put them out in different places, but they can all find their way to the front at the end of the lecture. That would be good. These are a couple of vowels of the kind that we use in EDDSAT. So just pass them around. And this is a circuit card Alpha and Elliott 903. 903 is before there were microchips, so it's individual transistors and resistors all connected together. That's a spare, don't lose it. This is some EDDSAT 5-hole paper tape, little thinner. Don't worry about preserving that one. And to go with the punch that's doing the rounds, these are the sticky patches you use to join paper tape when you stood on the tape and tore it, which was the thing I was expecting it to go wrong rather than the electronics to misbehave. So I hope that's given you some idea of what 1960s, 70s computing was like, and the way in which programming evolved very quickly during that decade. Let me start moving into more recent times. So by the mid-70s, the next development was home computers. And here Cambridge played a very important part, very important role. Many people will remember the BBC Micro. Indeed, I see several BBC Micro engineers and developers in the room. It was a very popular machine. One of the things that made it popular was it had a very robust implementation of a programming language called BASIC that meant you could do a lot with the machine, and it had lots of connectors on it, so you could hook it up to science experiments. You could buy all kinds of gadgets to plug into your BBC Micro. So it was a great thing to play with. The software was written by the young lad on the left in the corner, Roger Wilson, and much of the hardware was done by a chap called Steve Ferber, and those names will come back. Well, the founder of the company was Herman Hauser, well-known local entrepreneur. There was another outfit in Cambridge doing home computers, Charles Sinclair and his machines. Sinclair's model was different. His view was whatever it was, it couldn't cost more than £299. If you were lucky, you got a working computer for that. If you were unlucky, you got something that he'd sold you for £299. So it was very interesting what was going on at that time. Sinclair in some ways had a more Apple-like vision. He was selling to consumers. What could he sell them that did the least for the highest price? That was essentially his model, and that's the Apple model. They will sell you things for £400, £600 that don't cost that to make and aren't worth that. You can buy equivalent devices from other people, but the other devices don't have the cachet. They're not quite as fashionable. Whereas the Acorn products were much more selling to the users in terms of functionality, more like a kind of PC model of you get good value for money and you get a box you can do lots of useful things with. That development of home computing caused us huge problems in the computer lab because all the PhD students were going off building and playing with home computers. Wilkes was still head of department at that time, though Roger was very much his number two and positioning, I'd not say he was positioning himself, being positioned to become the next head of department. And so I remember sitting with the two of them and said, what can we do to get the students back in the lab? And we saw other people were investigating networking computers together. They'd chat to each other. We said, we better do a networking project. So they bring their home computers into the laboratory, at least they're in the building, and maybe we can encourage them to do some work. That led to the development of something called the Cambridge Ring, which is a local area network. Very successful at its time, used by several other universities in the UK. It didn't make it big time. That went to the Ethernet that you all use today when you plug wires into the back of your computers, or if you use Wi-Fi, Wi-Fi is essentially that same Ethernet but working with radio waves rather than across physical wires. But it did lead us to do some work in Cambridge, and there's starting to be a repetitive theme here. A system that Roger and I built with many others called the Cambridge Distributed System. All the Americans had grabbed hold of the home computer, personal computing idea. It's very liberating to have your own computer completely under your control, no data processor manager telling you what you can and can't do with it. You could program it, you could do whatever you like. That was very attractive. And the largest machines at that time were called workstations, 20, 25,000 pounds each, were really quite powerful computers. The computer lab certainly couldn't afford to buy workstations for its PhD students. The university couldn't afford to have workstations for all the people who wanted to compute in the university. So Wilkes, Roger, and I conceived of an idea of putting a reasonable number of computers in a rack and calling it a processor bank or a computer bank. And our users would sit in their offices with their BBC micros or their terminals like this thing here, and they would connect into that processor bank. They'd be given a computer for as long as they needed it to edit their programs, to run their work. If they had a BBC Micro, the editing could be done on the BBC Micro. They only needed a computer from the processor bank when they wanted to run some sort of calculation. And we'd store all their files on a big server called a file server that would be shared by everyone. Our American colleagues with their workstations thought this was a completely ridiculous idea. They really liked their personal computer because you could take ownership of it. But again, if I wind the clock forwards and I start talking about cloud computing, large data centers, it was precisely that vision. Of course, ours wasn't quite on the scale of a Google data center. This is yet another picture of Wilkes, by then known as the Old Man. Behind him is the processor bank. I think there were 3 racks of it with about 16 machines. But remember, this was 1978, 1980, so quite early on. The next development that was done in, by this time, Roger's lab in the networking area was to connect all the people who had Cambridge rings together by satellites. Remember, at this time in the 1980s, you could connect remotely using modems, those very slow things that whistled and burbled and you waited for your web page to appear over a matter of minutes. We got permission to use a satellite, and the satellite had very fast channels for sending data. The only trouble is they're quite long channels because the signal has to go up and come back again, so there's quite a delay. But once you've got the stuff moving, you can really shovel it through very quickly. And so over multiple sites, we built this system called Project Universe, never one to be understated in our project names. And we connected these sites together with what these days would be called fast broadband, and demonstrated that you could operate what we've been doing in a local laboratory environment on a national scale. And again, that was very breakthrough technology, Cambridge demonstrating things that others hadn't got to consider. Very quickly take myself into the more recent time. From about the middle of the 1990s, which is the end of that period of operating systems and networking research, the biggest change I saw in computing was the rise of something called machine learning and perception. And this was tackling a problem that previously had been called artificial intelligence, that was trying to get computers to do tasks that humans are good at. And when it was called AI, computers weren't very good at it at all. What happened round about the middle of the 90s was, rather than having the audacity to try and invent computer ways of operating that might mimic how the human brain works, when we didn't know how the human brain worked, it was a very conceited approach in AI. We just went for straight statistics. Can you analyze the data and do it that way? So for example, if you're trying to find in a collection of photographs the photograph with a car, suppose we show the computer millions of photographs and we tell it which ones have got cars in and which ones haven't. Can it build itself a statistical model based on all that data so that when we show it a photograph it hasn't seen before, it can do the statistical calculation and say, yeah, I think that one's got a car in it. And that's the machine learning idea. Well, one of the exponents of that was Karen Spark-Jones, another eminent fellow of this college, Mrs. Needham also, and have a long debate afterwards about who wore the trousers in that relationship. In many ways, Roger was the better known, but Karen certainly was an absolute leader in her field. And sadly, after Roger's demise, sadly in the sense that Roger couldn't share it with her, she did rise to prominence and got the recognition that she deserved. And she was sad that Roger couldn't share it with her. She'd been very supportive of him, he'd been very supportive of her. They used to co-write each other's papers and critique each other quite loudly. It didn't do to get caught in the crossfire. Karen's area was information retrieval, and she was the one who moved information retrieval into this world of using statistics. She realized if you had more documents and analysed them statistically, you could do a better job of solving questions like find me an interesting technical paper about the subject of operating systems or something like that. A Cambridge student, actually of Wheeler's, a chap called Mike Burrows, had worked in Cambridge on a system that analysed what we used to call news groups. These were online bulletin boards you could go to where people posted information about computers and technology. He built a system so you could search that, because you're always thinking, is there someone who's written a solution to the problem I've got with this programming language or something about this computer? And so he took an interest in search. When he left the computer lab, he went to join an American research lab, the Digital Research Center in Silicon Valley, and he wrote a search engine called Alta Vista. And again, the older amongst us remember that Alta Vista was what became before Google, and introduced us the idea that on the internet, if we could search all that content, we didn't have to remember all these strange URLs and carefully write down where things were. We could just ask the internet a question and it would give us an answer. That work was done by Burrows, and Karen was one of his major collaborators. She had quite a significant input to Alta Vista and that ongoing work, and that helped establish her relationship. Rattling on, where are we now? I think the current decade, the one just ending, has all been about mobile computing, and not that kind of thing, but this kind of thing. Remember those two chaps at Acorn, Roger Wilson and Steve Ferber? While still working for Acorn, as Acorn was developing its range of machines, they designed their own processor. Their reasons for doing that was to bring the cost down. They wanted to have their own processor design with spare space on the chip that they could put on custom things that their computer needed. That was the genesis of the idea. To make a very long story short, Acorn folded because the home computer thing kind of went away. It was taken over by personal computers. But the Acorn RISC machine became ARM, which has become a huge company. ARM doesn't actually make chips. All they do is design them. And people bite their arms off to license those designs at huge fees. And that ambition to have an inexpensive but fast chip with spare space absolutely works for people who are trying to build things like tablets and mobile phones, because they want something that doesn't consume very much power, so the battery lasts a long time. They want something that has spare space so they can put on the circuits to work the radios and everything else, and they want to be able to customize it. So that's been a very successful model. So to wrap up, where do I think things are going next? Well, the jargon phrase is the Internet of Things. Just about everything has a computer in it, and they're all starting to talk to each other. And so that has all kinds of interesting implications in areas like robotics, how systems work in our houses. We're already seeing navigation systems, a whole variety of devices that can talk to each other. You combine that with machine learning, where all the data that's been collected can be analysed and used and give us very intelligent, very advanced systems. There's a whole other lecture and discussion about how we manage that world. There's a whole debate about will the machines take over. I don't think they will, because arguably we can do more than computable functions, so we can make them terminate. And the thing which gives me great hope as my final piece of Cambridge technology, and this very Cambridge-oriented view of computing, is a system called the Raspberry Pi. This was conceived of a couple of years back as a piece of kit to get school kids back on computers with the same passion that the BBC Micro had. It's a tiny computer on a circuit board, and it's surrounded by things you can plug other technology into. And if you go on the net and look what you can get for the Raspberry Pi, there are kits to do all kinds of things, simple robots, weather sensors, temperature sensors, and that's, I think, encouraging a whole new generation of kids to get as inspired and excited about computing as I was when in 1968 my maths master said, why don't you go to the college and run the programs for us? You might enjoy operating the machine. Thank you very much.